Welcome to the walkthrough for the specification, skeletons, and tests, part 2 of assignment 4B. The purpose of this assignment is to deepen your experience using Java functional programming features and their integration with Java reactive streams in a networked computing environment. In particular, in this assignment, you'll develop an app that uses the Project Reactor implementation of reactive streams to obtain, transform, and store images asynchronously in conjunction with a set of reactive microservices accessed by a Spring Web Flux. The code you write has a GUI and runs as an Android client app that can either perform all image processing locally on the client device running Android, or perform all the image processing remotely using reactive microservices that can be deployed on one or more servers and implemented via Spring Web Flux. Please use this GUI along with the unit test discussed below to help evaluate and debug your solution. The following resources may be helpful in completing this assignment. An overview and comparison of Java reactive streams and streams is available here, and tutorials on Project Reactor appear here and here. Naturally, we'll cover all this material in class, which will be available in my YouTube CS253 playlist here. Before you complete the initial submission of Assignment 4B, you'll need to do the following. Revise your implementation of Assignment 4A, taking into account my review comments, since it forms the basis for the client app in this assignment. Please come to office hours or post questions on Piazza if you have any questions about your Assignment 4A solution. The image crawler app is packaged as a project using the latest version of Android Studio. This app is written in both Kotlin and Java and demonstrates many Android capabilities. For the purposes of Assignment 4A, however, you only need to be aware of the following directories. Image crawler source main Java edu Vanderbilt image crawler crawlers, which contains the skeletons you need to fill in, as described below. Image crawler source test, which contains a set of unit tests that exercise the features you'll be implementing and are used to evaluate whether you've correctly satisfied this assignment's requirements. An app source Android test, which contains an Android Studio instrumentation test that runs your app automatically. To compile this code, you need to use the provided Android Studio project. You can run this project by clicking the green Run App button in the Android Studio IDE, which should automatically select an Android emulator to run, assuming you have one created. The app's minimum API is 29, so you need to select an emulator that uses an API greater than or equal to 29. I recommend API 30. If you don't already have Android and an Android emulator, you can create one by clicking on the AVD Manager button in the Android Studio IDE. You'll need to modify several files containing the skeletal Java code by completing the to-do you fill in here task to provide a working solution. Please don't change the overall structure of the skeleton, just fill in the to-do tasks, and don't delete the to-do tags. In particular, you need to finish implementing the following to-do tasks for this assignment in the image crawler crawlers folder. First, you'll need to complete the to-do tasks in various methods of the image crawler crawlers reactor-crawler.java file to obtain, transform, and store images. This class uses flux and mono operators in the Project Reactor framework to perform an image crawl asynchronously, starting from a root URI. Depending on the parameters used to run the app, images from HTML pages reachable from the root URI are either downloaded from a remote web server or read from the local file system, transformed locally, and the transformed results are then stored in the local file system on the Android device. Likewise, these parameters also determine whether all image processing is performed locally on the client device or remotely using reactive microservices deployed to one or more servers. You'll also need to complete the to-do tag in the student.kt file to set the type field to include just graduate or undergraduate, depending on which version of the assignment that you're implementing. Your solution should use no loops or if-else statements in this assignment, and instead use the Project Reactor operators and functional programming features. Likewise, there should be only one call to block. Your solution will be considered correct if it passes all the unit and instrumentation tests, is commented thoroughly, and addresses my review comments. Skeleton code from this assignment is available here on my GitHub account. Now that you've set up your GitLab account, you can pull the skeleton code into your repository, read it carefully, and complete the to-do markers. The unit tests in the image crawler source test folder are provided to increase our collective confidence that your implementation is working as expected. You'll need to use the Android Studio GUI to run the unit test locally on your computer, as described here. As usual, testing only demonstrates the presence of bugs and not their absence, so don't rely solely on the unit test to detect problems in your code. This assignment is more complicated than the previous assignments, since it requires deeper knowledge of Project Reactor and remote communication with reactive microservices via Spring Web Flux. In particular, the asynchronous nature of reactive streams may take some time to get accustomed to, so please start the assignment soon. Ask questions in class, office hours, and on the discussion forums. As usual, the app, image crawler skeletons, and unit tests are extensive, though you don't need to understand them all to complete your solution successfully. Now that we walked through the specification for part 2 of assignment 4B, let's go ahead and take a look at the skeletons. If you click on reactorcrawler.java, you get a chance to see the skeletons. As you'll see, the reactor crawler class uses Project Reactor Flux and Mono reactive types to perform an asynchronous image crawl starting from a root URI in a pool of threads. Images from HTML pages reachable from the root URI are downloaded from a remote web server or from the local file system, transformed, and then stored in files on the local Android device that can then later be displayed to the user. Likewise, image processing is either performed locally on the client device or remotely using reactive microservices deployed on one or more servers using Spring Web Flux. Let's take a look at the methods that you have to fill in now, starting with perform crawl, which is the main entry point method that recursively crawls the given page and returns the total number of processed images. The implementation here will need to call the crawl page async helper method to perform the crawl asynchronously, and then get the result of that, get a count of the number of images downloaded and processed, wait until all the processing is done, and then finally return the result as an int value. If any errors or exceptions are encountered, then a 0 value is returned, indicating that there were no images processed. And you can take a look here, kind of giving an overview of the steps to be done here in this particular implementation. Let's now go ahead and take a look at crawl page async. This takes a page URI and a depth, and it'll return a flux stream of images from this page and all page links that are recursively reachable from it. An empty flux is returned if the depth limit of the web crawling is reached or if the page URI has already been visited earlier. This method should use flux operators like just, filter, map, and flat map, and this latter operator should call the helper method images on page and page links async. And again, there's kind of some comments here to give you an overview of the flow that should be taking place here. Let's now go ahead and take a look at the images on page and page links async method, which takes a page and a depth. And this returns a flux stream consisting of all the images on the page and any images linked on it. This method should call the images on page links and images on page helper methods and use flux operators merge with and subscribe on to merge all the images into a single flux stream using a parallel scheduler. Let's now take a look at the images on page links async method, which takes a page and a depth. This implementation needs to create and return a flux stream consisting of images that have been downloaded and transformed. This method should call the crawl page async helper method recursively, that was defined earlier, and use flux operators from iterable, flat map, and subscribe on to perform the processing on the parallel scheduler. And if you take a look again, there's some hints here about the steps involved here. Let's now take a look at images on page async, which takes a page as a parameter. This creates and returns a flux stream for this page using the methods getPageElements as URLs, downloadImageAsync, and transformImageAsync, as well as it uses flux operators like flatMap and fromIterable to perform processing. The flatMap operator could be called more than once in this implementation. This implementation is actually really quite straightforward. Don't get too carried away and try to do complicated things, which you could take a look at from the frequently made mistakes for assignment 4A to get some hints about what not to do. The next method is the downloadImageAsync method, which takes a URL, and this implementation should create and return a mono instance that emits the downloaded image at the specified URL. This implementation should call the helper method getOrDownloadImage, as well as use mono operators like fromCallable, subscribe on, and map not null to perform processing on the parallel scheduler. And again, there's some hints about the flow of this particular stream. The next method is transformImageAsync. This takes an image as a parameter, and I provided the implementation here. It basically does a call to see whether or not the image should be transformed remotely using reactive microservices or transformed locally. And we'll take a look at both those implementations. You have to implement both of those methods. This implementation is slightly different from assignment number 4A because now we're handling both local and remote processing. Let's take a look first at transform image locally. That takes an image, and the implementation will process and transform the image locally and return a flux stream of transformed images because, of course, there will be multiple transforms applied. This method should call the create new cache item and apply transform helper methods, as well as use flux operators from iterable, subscribe on, filter, and map not null. And again, there's kind of a flow of the various pieces in the stream that you should be calling to give you some hints. Now, finally, we get to transform image remotely. This is the method that's really the brand new method from this assignment. And that, of course, is going to be connecting to the server that you have to implement, the transform reactive microservices implementation, which is going to be using Spring Web Flux and Project Reactor to do the implementation on the server side. Transform image remotely is essentially a proxy, if you will, that takes the image and it will process the transforms remotely, and it'll return a flux stream of transformed images. This method should call the build multipart body part method, get transform names, and apply reactor transforms, and create image helper methods, as well as use flux and mono operators such as flat map, many, and map, respectively. And if you take a look, I give you a bit more of the structure here because it's a little bit complicated to get started with. But basically, you'll make a call to the get remote data source helper method, to the get API method that's part of that, and that'll return the transform API that basically is going to be what's used to call the server remotely. And then you're going to call the remote data source helper to build a multi-part body part that contains the image bytes, and you have to go ahead and fill in the implementation to do that. And then you'll go ahead and call a superclass helper method to get the list of transforms. You could go take a look and see how that's done. That's done in various other ways and other implementation strategies you've done in earlier assignments. And then you'll call the API method that builds a flux stream of transforms. And once everything's up and going, this stream will use microservices running on the server to concurrently run all the transform operations remotely. And so here again, you'll call that remote data source method that applies all the transforms in parallel on the image remotely. You'll take what comes back, which will be a mono to a list of transformed images, and then you'll convert that to a flux of transformed images, and then you'll create an image instance to return back to the caller. And so you'll have to kind of poke around and look at some of the helper methods to see how that you're going to do that. The implementation here is a little bit wonky because of the fact that on Android, you can't actually get a flux back directly. So instead, we have to do the next best thing, which is get a mono to a list of transformed images, which we then will go ahead and convert into a flux of transformed images locally. Hopefully at some point, Android will remove that particular limitation and things will be a little easier to work with. If you go over here and take a look at get remote data source, you can see what that does. That goes ahead and gets the remote data source. And this has got some really cool things that you can take a look at if you want to see how all this works under the hood. This is basically what's being used with adapters to be able to communicate from Android to the server side. So that's basically what you'll have to do here. You can see some of the helper methods here, like build multi-part body part, where you pass in various parameters. And there's some other stuff here that's used internally, the build API and so on and so forth. And here's the apply transforms method. You don't necessarily have to know all the details of how that works under the hood, but this is the method you'll be calling in order to get things to work. And here's the transforms API. This is basically using a neat little trick that will automatically generate all this code for you. So you don't have to do this, and it'll make your life a heck of a lot easier. This is the method that is going to be actually called with the various parameters that are encoded properly. Again, these are sort of implementation details. You don't have to know all the nitty-gritty details of how this works under the hood, but this is what's happening so that you don't have to worry about that stuff yourself. So that's basically a walkthrough for the skeletons for assignment 4B, part 2, which is the client side of all this stuff. So these are where you need to go to figure out how to implement the transform image remotely method. Now that we've walked through the specification and skeletons for part 2 of assignment 4B, let's go ahead and run the unit tests. As usual, you come into the test folder and click run the tests, and that will go ahead and build the tests. Since all the tests in this class are cumulative, there's going to be a heck of a lot of tests, as you might imagine, because we're going to be running the tests for assignment 1, assignment 2, assignment 3, and now assignment 4. As you can see here, all these tests are running, And not surprisingly, because this is my implementation, everything works just fine. And that's exactly what you should see as well. It's very important to make sure that all your tests also work properly for all the different assignments you've had, because your final grade is going to be based on the cumulative result of running all the tests. So don't neglect to make sure everything is working perfectly, and everything should be green. And if everything's green, that's a good sign, because that means you're going to do well on your final grade. Now that we've shown how to run the unit tests, let's go ahead and see how to run the app itself. As you can see, I've actually got two windows open here. On the left-hand side, I've got Android Studio, and on the right-hand side, I have IntelliJ. And this is the way I've done things. I've gone over here to the microservices application tab, and I clicked the green run button, and that went ahead and started up all the different microservices. So we have the Eureka application, we have the main application, we have the Grayscale microservice, the Sepia microservice, and the Tint microservice. So all of those things are now up and running. I pre-started it because it takes a little bit to run to get them started. And then I go over here to the Android Studio app, and you can see I've picked Project Reactor implementation, and I've made the transforms be remote, which means they're actually going to be performed by the microservices running over here in IntelliJ. So I've kept the images local just because I don't feel like going out to the web to get those. So now I come over here and I click on the download icon, and as you can see, things start to run. And what's happening here is that all the processing that's being done is being processed by making the calls to the microservices applications over here where they're actually doing the work. And that's what's processing the requests. And you can see that everything's kind of cranking away and doing fine. I could also come back over here if I chose and make the transforms be local instead of remote. And let me go ahead and re-download everything. So now we're going to go ahead and start up. You can see it's doing the processing. And in this case, because it's doing everything locally, it'll probably take actually a little bit less time to run just because of the way that the processing is set up. You can see it took about 12 seconds to run instead of 18 seconds. If I were actually running in a real server with higher horsepower, I'd probably see a better speed up from doing things remotely versus locally. But you can see how easy it is to toggle back and forth between local and remote. So I recommend you try out the way the app works and make sure that your client can connect to the server and do the processing in the microservices.